All right, let's talk about functions. You already know they're super powerful tools in math, right? But what if I told you we could level them up? Today, we're going to dive into how to combine functions, adding, subtracting, multiplying, and even dividing them to create brand new, more powerful ones. Let's get into it.
You know how to add 2 plus 2. It's second nature. But what about adding f of x plus g of x? That looks a little more intimidating, doesn't it? Well, what if I told you it's pretty much the exact same idea? The answer is a huge yes, you absolutely can, and I'm about to show you just how simple it is. So here's our game plan. First, we're going to lock in one huge idea. Functions behave a lot like numbers. Then we'll get our hands on the 4 basic operations that will be our main tools. After that, we'll see it all in action with real examples, and I'll even point out a few common traps so you can avoid them. And finally, we'll answer the big question. Why does this even matter?
Okay, let's jump into our first big idea, that functions really do behave just like numbers. All that simple arithmetic you've mastered over the years, that's about to become your secret weapon for handling these more complicated-looking expressions.
Here's the core concept. Don't let the whole f of x notation throw you off. When we talk about combining functions, all we're really doing is using the same old operations you already know: add, subtract, multiply, divide, on these algebraic expressions. You're just taking 2 functions, putting them together, and getting one new function out. So if we're going to treat functions like numbers, what does that actually look like in practice? Let's break down our toolkit. These are the 4 basic operations that are the foundation for everything we're about to do. You know, what's great about this is how straightforward the notation is. That stuff on the left, like f plus g of x, it looks fancy, but it literally just means take f of x and add g of x to it. That's it. And that same simple logic works all the way down the list for subtraction, multiplication, and division. This table right here is your ultimate cheat sheet. Now, hang on. Before we start smashing functions together, we need to talk about one really important rule of the road. It's called the domain. You can basically think of the domain as the official list of all the allowed x values that you can plug into a function without breaking math. And when we make a new function, we got to figure out its new set of rules. So for adding, subtracting, and multiplying, the rule is pretty chill. The domain of your new function is just wherever the domains of the original 2 functions overlap. Easy enough. But division, well, division always has to be special, doesn't it? We have to remember the golden rule. You can never divide by 0. So for division, you find that same overlap, but then you also have to find any x values that make the bottom function, g of x, equal to 0 and kick them out. Okay, enough with the theory. It's time to see how this actually works. Let's get our hands dirty and walk through a few examples together. Let's start with addition and subtraction. We've got our 2 functions here. For the sum, we just line them up, add them, and combine the like terms. Simple. For the difference, it's almost the same, but look closely. We put g of x in parentheses. That little detail is absolutely critical, and you'll see why in a bit. All right, next up, multiplication. We take our 2 functions, multiply them out. You might remember the FOIL method for this, and that gives us a brand new function. From here, we can plug in any number we want. So if we want to find out what happens when x equals 3, we just substitute it in. So we get 3 squared minus 3 times 3 minus 10, which is 9 minus 9 minus 10, which leaves us with negative 10. And that's our answer. See, the process is logical. You combine the functions first, and then you evaluate. Now, for division, this is where things get interesting. We put f of x on top and g of x on the bottom. Now, you might notice we can factor the top. And when we do, look at that. The x minus 3 terms cancel out, leaving us with just x plus 3. But, and this is the most important part, you have to look back at the original problem. Before we canceled anything, the denominator was x minus 3. That means x can never be 3, or we would have been dividing by 0. This is a point I really want you to remember. Even after you simplify, and the problem seems to disappear, the original domain restriction is permanent. It rules forever. Think of it like a ghost. Even though you can't see the x minus 3 on the bottom anymore, it still leaves a permanent hole in the graph at x equals 3. All right, let's talk about the common mistakes. I want to show you the traps that people fall into all the time, so you can just sidestep them completely. This right here is probably the #1 mistake I see. Remember those parentheses in the subtraction problem? This is why they matter so much. You have to subtract the entire second function, which means you have to distribute that negative sign to every single term.
If you forget, like on the left, you get the wrong answer. But if you do it correctly, like on the right, you'll get it every time.
And let's just hammer this point home one more time. That domain restriction from a division problem, it's permanent. It doesn't matter what your final simplified answer looks like. If x equals 3 was a problem in the beginning, it's a problem forever. Period. So, after all that, you might be asking, okay, but when am I ever going to use this? And that's a fair question. Turns out this stuff pops up in the real world more than you'd think. Think about any company. How do they calculate their profit? It's simply the money they bring in, their revenue, minus the money they spent, their cost. Well, both revenue and cost can be described with functions. So the profit function is literally just the revenue function minus the cost function. It's function subtraction, plain and simple, and it's used to run businesses everywhere. So we've seen we can combine functions in all the ways we're used to with numbers. But this kind of opens up a new question, doesn't it? We've been putting functions next to each other. What would happen if we tried to put one function inside another one? Well, that's a whole other story, and it's a very powerful idea for another time. Thanks for watching.